You may have wondered how one might trap plasma. Well, the answer is a magnetic bottle. So, if charged particles enter a magnetic field, not perpendicularly, but at a slight angle, what we get is a circular motion component. But since the velocity here is not perpendicular to the magnetic field, it has a parallel component. That parallel component experiences no force. So as the perpendicular component to the magnetic field results in a force that moves it in a circle, the parallel component of the motion is unaffected and it produces no force, so you get helical motion. So that's how you produce a helical path for a charge in a magnetic field. So that's good. You're constraining the motion of the charge to this helical path. But then it's gone. I'd like to constrain it to a smaller region of space. Well, we can do that. That's what happens if the magnetic field is a little more complicated, like in the Van Allen belts of Earth. We actually get charged particles that can escape. This graphic kind of shows the whole picture, most of it at least. It might be more clear than the little breakdown I'm going to show you, but you can refer to this as I go through the description here. So we have a magnetic field of a strange shape. And we have the basic helical motion phenomena that we just discussed. So here's the particle, the charged particle, moving around in a helical path. But there's a difference in that because of the shape of this changing shape of the magnetic field, we have forces that are acting in such a way to trap it. So let's see how that works. So here's the motion initially, or at this particular point, the velocity. It's got both a perpendicular and parallel component to the magnetic field. So now here's the direction of the magnetic field, okay, like this. The magnetic force is perpendicular to that, so that's pretty good. Well, that perpendicular force has an inward force and a force in this direction. So I just broke it down into its components. We see the same thing here. That results in an acceleration toward the center, or in this direction, the acceleration of the particle because of this force. So it's being accelerated in this direction. Well, now let's consider when it's on the other side. Okay, if it's moving in this direction again, we have the magnetic force perpendicular to the magnetic field. We have a inward and a parallel, or a force, parallel and horizontal, I guess I'll say. And you'll notice that that force is in the opposite direction as the one symmetrically on the other side. So that results in an acceleration inward. So that's the scenario that we have. Now, because of those forces toward the center, and notice at the center point, everything is perpendicular. The force is perpendicular to the velocity. There is no acceleration at that point. So what happens to the particle? It'll be trapped inside this magnetic field region because it's always being accelerated toward the center. You see that particle? You probably don't.
That was fun, but I don't like being trapped in here.
Well, anyways, you can get out of that trap if you just reduce the geometry of the magnetic field. Oh, sentient particle. Anyway, I was trying to show, not very well, the helical and the back and forth oscillatory motion there. I don't think it showed up very well. But this, in a nutshell, is the function of a magnetic bottle, and we're going to see now how that applies to the Earth and its magnetic field. So shown here is a simplified diagram of the basic structure of the magnetic field of Earth. We have magnetic South Pole up here. We have magnetic North Pole underneath. The geographic poles are also not coincident with the magnetic poles. So North Pole magnet down here produces magnetic field lines looping around. Put a compass in that field and it'll point toward the north, because it's really a south magnetic pole that the north pole of the compass is being attracted toward. Now, in a little more detail, it's been understood that the magnetic field of Earth is a little more complex, but fundamentally there's two belts called the Van Allen belts of magnetic fields that encircle the Earth a long ways away. And charged particles from the sun and elsewhere can come in and enter from any direction here and enter into the magnetic field at slight angles, such that, notice the geometry of these magnetic fields, how they're bent, and it literally produces helical paths trapping the charged particles in the inner and outer belts of Earth's magnetic field. This graphic shows it in even more detail, and it's you see the inner Van Allen belt here. It's about 1,000 to 8,000 miles from the Earth, and that's about the radius of the Earth. And then we have the outer belt. This whole thing here is the outer belt, and it's 12,000 to 25,000 miles. So this shows the size of these belts in perspective. We actually have a couple of satellites that are passing through these Van Allen belts, orbiting around Earth, monitoring the particular strength of the magnetic field at different times. In fact, just recently, or here early in 2013, they've discovered evidence for another belt in between these two. But this is the overall structure. And what's interesting is the result of charged particles coming into the vicinity of Earth. Not only do these belts protect us from their dangerous potential, but also they lead to a very beautiful display that you've all heard about, at least in passing, if you haven't experienced it directly and personally. So the visual beauty I'm talking about is manifested in the Aurora Borealis, or Aurora Australis, and just focusing on the Borealis in the northern hemisphere. This shows the region on Earth where the charged particles from the sun that get trapped in the Van Allen belts, they come spiraling in. Those charged particles hit the oxygen and nitrogen molecules in the air, and that produces electron transitions, activates, energizes, excites the atoms, sometimes ionizes them, and as those electrons cascade back down in their atoms, they emit photons of various wavelengths of light to produce the visual displays known as the Aurora Borealis. And here is a satellite image of that region. Now, the magnetic field coming in is centered around the magnetic pole, not the geographic pole. See how far off they are? The magnetic pole is actually in Canada. So when the sun goes ballistic with coronal mass ejections, flares, eruptive prominences, and other phenomena, then the plasma ejected from the sun is significant enough that it puts so much pressure on these belts that those charged particles really significantly get into the atmosphere. And once they, as I said, hit those atoms and molecules in the air, they result in those energy transitions. So here is a view from Alaska. In this particular case, you'll notice the kind of circular region of the Aurora Borealis. Notice that it's the center of this would really correspond to about here. So we're seeing this really high in the sky, so we can actually see that circular geometry in this particular case. That's not always true. And here we see a band of the primary auroral activity across here. Based on how high it is, you see it from this line to this line. I lived around here, right on the edge of this thing, up in Alaska, 80 miles north of Valdez. It was actually probably closer to here. In any case, sometimes I see the whole sky lit up, but seeing aurora was a common experience. And it's very easy to see when the sun is active and you're living in the north. Pretty common phenomena. This image here is typical of the kind of display that I would see quite frequently. Here's another one. Again, you can see this circular shape. So, that clearly manifests the basic geometry of the magnetic field entering the Earth as well. There really are a lot of colors that the aurora can reveal. Notice here's the Pleiades, a little grouping of stars. But the colors certainly enhance the visual appeal. Look at those colors. Oh my goodness. I don't think I've ever seen that bright of color saturation. I'm not sure if this is enhanced or not. That's a little atypical. And there is another one. And these colors will be like little pencil beams just dancing around, dancing all over the place, shimmering up and down. And I hope you have the opportunity to see something like this someday. And yet another one. And now for the next couple minutes, I'd like you to sit back and enjoy a tribute to the amazing power of our incredible sun.